right. Good morning, folks. Happy Thursday. I hope everyone is doing well this morning. You made it through your first of 8 weeks of Calc 2, and hopefully you're feeling, at least if it's not delightful, that it's manageable. I wanted to start off today with a couple announcements. So we're going to take a look at Canvas real quick, and then we'll hop into our lesson for today. Okay? All right, so hopefully you are feeling pretty comfortable with Canvas now and sort of where you might find things. And so one thing that I wanted to point out for today is that, so we're in chapter 9, we're in section 9.4. So if you go to 9.4, today we're gonna be looking at partial fractions. Okay, now that was something that you learned in pre-calc, but I know that it's, you know, pre-calc was at least 2 classes ago for folks, and so that's kind of a long time. So today's lesson is gonna go over a little bit of partial fractions, but we're mostly gonna focus on the calculus end of how it applies to our integrals. So if you feel like you need a review on partial fractions, I took my notes from my pre-calc class. So if you look here, it's got a review on partial fraction decomposition. You've got blank notes, complete notes, as well as the videos if you want to go through a few examples, okay? So if at the end of class you're feeling a little overwhelmed with the partial fractions, that could be a really good resource for you. Or I know many of you already have other YouTube channels that you really like to watch and help explain math to you, so you're totally welcome to use those as well. I just wanted to include a few resources for you right here, okay? So that's for our lesson today. The other thing I wanted to let you know is, and I don't think I can share this without sharing someone's grade, but all the quiz 1s have been graded. And if you look at your assignment for quiz 1, you should see a file attachment, and that file attachment should be the graded version of your quiz 1. Okay, I had a little bit of an issue yesterday syncing my Notability between my computer and my iPad, but I think that was fixed this morning. So if you didn't get your quiz back electronically last night, you should have it attached to your Canvas file or your Canvas today, okay? If you have any questions about the grading, someone already pointed out that I made a huge mistake on theirs, please let me know. 60 plus quizzes is a lot to go through, and so of course there are going to be mistakes, and if you let me know, we can certainly take care of that, okay? All right, any questions before we get started? All right. So if there are no questions right now, then we're going to go ahead and jump into our 9.4. So again, you can find the blank notes on Canvas, and that's what I'm going to be sharing on my screen with you. And at the end of class, if anybody has any questions on quiz number 2, feel free to hang around and ask those questions. I think it was useful for those of you who did, so feel free to do that, okay? Alrighty, so here we go. 9.4, integrals of rational functions. All right, so we're going to start off with a what we know and a what's new, a pattern that hopefully we're getting pretty comfortable with at this point now. And we're going to take a look at this one question, what we know. And so we've got the integral of 3 over x dx minus the integral of 1 over x plus 3 dx plus the integral of 2 over x minus 1 dx, okay? So we've got 3 separate integrals here, and they're all relatively straightforward ones. And so what I want to do is go ahead and show how we would solve this one just as a review, and then we're going to take a look at the what's new, okay? All right, so what we know. If we have a question like this, then one thing that we might notice is that we could use that idea where we take the constants and pull them out to the front. Specifically, we could take this 3 and move that out to the front. And we could take this 2 and move that out to the front, okay? So let's do that first and see what we get. 3 times the integral of 1 over x dx minus the integral of 1 over x plus 3 dx plus 2 times the integral of 1 over x minus 1 dx. So when you have these 3 integrals, I would say that the first one is a pretty clear case that is not going to be the power rule, okay? This is the one exception to the power rule, and I really want us to remember that, okay? So this one right here is going to be the natural log, okay? So it's not the power rule. And so when we integrate this one, we're actually going to get 3 times the natural log of x, okay? Now, for the other two, with it being 1 over something, like x plus 3, and 1 over something else, x minus 1, we can also use the natural log, but technically, we have to use u sub as well. And so I want to show you this u sub right here, because it turns out in this particular case, if you happen to forget u sub, it doesn't actually impact your answer. However, we might encounter some other sort of simple cases where when we forget u sub, it does throw our answer off. So I just want us to get a kind of into the habit of checking for u sub, okay? So if I use u sub for this one, that would mean that my u would be x plus 3, and my du would be dx, okay? So what that means is when I substitute, I actually end up with the integral of 1 over u du, okay? And when I take the integral of that, that's just going to give me this next part, minus the natural log of u, which is x plus 3, okay? So this right here, we need a u sub to do that integral. And the same is going to be true for the last fraction. We're going to need to use a u substitution there as well. Now you can use the letter u, I think, to make things, in an attempt to make things easier. You folks let me know if it's actually easier or not. I just used a separate letter. I said v equals x minus 1 and dv equals dx. And then I was able to write the second integral as 2, the integral of 1 over v dv, okay? You can use u as well. Some people do like a u sub 1 or u sub 2. I just didn't want you to think that like the first u was the same as the second u, okay? But either way, once we make that substitution, we'll be able to use u sub to find that second integral, and we'll get plus 2 times the natural log of x minus 1, and then we'll seal that off with a plus c, and we'll have our answer, okay? All right, so with this here, are there any questions so far on this first example? Okay, thank you, Carl. I appreciate that. All right, so the what's new, all right? We go from something that is fairly straightforward. We've got 3 integrals. We use u sub, but it's so simple, straightforward. We don't even need to divide anything, to this kind of scary looking thing here, okay? Now, what we're going to do is use this problem to review the idea of partial fraction decomposition, okay? So in partial fraction decomposition, one of the things that we want to do is we want to make sure that we completely factor the denominator, okay? So let's go ahead and factor that denominator first. So I'm going to keep the numerator the way it is. And when I factor the denominator, before I start panicking that it's a cubic on the bottom and that I don't know how to factor a cubic, we should always look for a greatest common factor. Okay, that's kind of a really good way to start factoring. No matter if it's quadratic or cubic or fourth degree, a quartic, what you want to do is try and find a greatest common factor. And when I look at all three terms in the bottom, I notice that they all share an x. So I'm going to factor that x out. And then we end up with x squared plus 2x minus 3. And don't forget that dx, okay? Now what we've done is taken a cubic and turned it into a linear, which is the x, and then a quadratic, which in this case also happens to be factorable, okay? And so we're going to continue factoring, and we'll get 4x squared plus 13x minus 9 over x times x plus 3 times x minus 1 dx. Okay. And so what we have here in this first line is we've started to set up for a partial fraction decomposition. And so what we want to do is turn this question into something that looks like this: the integral of a constant over the first denominator, so x, plus a constant over the second denominator, plus a constant over the third denominator. Okay? Now, if it were in this form, a over x plus b over x plus 3 plus c over x minus 1, then it would look like an integral that we could integrate, because we could do each part by itself, and then we would be able to get our answer, okay? And so what we're going to do now is find a, b, and c. All right, so we need a and b and c to solve. And so what we're going to do is we're going to take our factored form right here, okay? And we're going to rewrite this. So 4x squared plus 13x minus 9 over x times x plus 3 times x minus 1. Great question, Mariah. We don't need a dx next to each one because we're still considering it as one integral. As soon as you write more than one integral symbol, then you need more than one dx. Okay, so what we're going to do is we're going to say that our factored fraction is equivalent to a over x plus b over x. Leave more room. Plus c over x minus 1. Okay? So we want the thing in the blue box to equal the expression that we want, that we know how to integrate. And so our job here is really to find a common denominator on both sides of this equation. Okay? That's why I left so much space in between each fraction. So when I look at the first fraction, I notice that it has an x, just like this one does. But what it's missing is an x plus 3 and an x minus 1. Now, if I only write that x plus 3 and the x minus 1 in the denominator, then I'm changing the question. But if I write it in the numerator as well, then I've actually preserved the form of the equation, okay? So now let's take a look at that second fraction. What does that second fraction need in order to make the denominator the same as the other side?
X minus 1.
Yeah, exactly. We need an x, and if we have an x down here, we need an x up here, and an x minus 1, and then an x minus 1, okay? And then the last one, we're going to need an x and an x, and an x plus 3, and an x plus 3, okay? As soon as you see that both denominators, both sides of the equal sign have the same denominator, you can get rid of them. So as soon as you've matched all the denominators, you can cross those out. And the equation that we're actually going to be working with is just the numerator, okay? So I'm going to take the time to write it out. So we'll have 4x squared plus 13x minus 9 equals a times x plus 3 times x minus 1 plus bx x minus 1 plus cx x plus 3. And now what we're going to do is solve for a, b, and c. Okay, now there's a few different ways to do this, but my goal is to show you what I think is maybe the most efficient way to do each problem. Okay, so in a case like this, when every single fraction we have has a linear denominator, so like x is linear, x plus 3 is linear, x minus 1 is linear. If everything in the denominator is linear, what we can do, instead of setting up a system of equations, is be really clever about the numbers we try for x, okay? So here's what I mean by that. I'm going to say that we let x equal 0, all right? And when I mean x equals 0, I mean x equals 0 on the left-hand side and x equals 0 on the right-hand side. So let's plug in 0 on the left-hand side and see. I get 4 times 0 squared plus 13 times 0 minus 9. And when I plug in 0 on the other side, let's see what we get. A times 3 times negative 1, because I plugged in 0, plus, what happens to the b term when I plug in 0?
Becomes 0.
It goes to 0, yeah, exactly. So plus 0, and guess what's going to happen to the c term as well? That's going to go to 0. So by choosing the number 0, what we actually ended up with is an equation that says negative 9 equals negative 3a. And when we solve that, we get a equals 3. Okay? What would be another clever number that we could try plugging in for x?
Negative 3.
Negative 3, I love that. All right, so let's try negative 3. So when I plug in negative 3, we have to plug in negative 3 to that left-hand side. So we've got 4 times 9 plus 13 times negative 3 minus 9 equals, the only term that's going to be left is the b term, right? We'll get a 0 plus b times negative 3 times negative 4. And we should end up with negative 12 equals 12b, or b equals 1. Okay. So we've got a and we've got b. We just have one last constant to find, and that's going to be our c. And so again, we can pick a number, be clever about what we pick. And in this case, if I pick 1 for x, I'm going to be able to find a value for c. So let's let x equal 1. And I'll get 4 plus 13 minus 9 equals 0 plus 0 plus c times 1 times 4. Or I'll get 8 equal, whoa, 8 equals 4c, or c equals 2. Okay.
B equal
Negative.
negative, yeah.
Yeah, I just found that myself. Thank you. All right, so really great point here. Always double check your signs, okay? Double check your signs before you start integrating, because if you make a mistake here, it's going to carry all the way through. Don't be like Judy. Check your work, okay? So we've got our 3 variables now, or constants. So we've got our A, our B, and our C. And when we fill them into our question, we're going to get the integral of 3 over x plus -1 over x plus 3 plus 2 over x minus 1 dx. And if we think back to our original problem, this is exactly our original problem, okay? And so we know how to solve that from here. So we're not going to solve it again. But what I wanted to show us was that we know how to integrate a bunch of different things, but sometimes we have to do some prep work to make it ready or make it into a form that we can integrate, okay? So this is going to be the theme of today. And I think we only have 4 examples today because some of them are kind of long, but that also leaves some time at the end of class in case folks have questions about quiz number 2. I'm happy to stick around and answer those questions, okay? So let's go ahead and get started. Okay? There are a few different cases that I want us to be aware of as we work through the problem, all right? So let's look at these different cases. When we set up our partial fractions, we need to think about whether we're having an A on the top, or sometimes we need a linear term on the top, sometimes we need a quadratic. And so we really want to make sure we know what to put on top. It's not always going to be just a constant, okay? So this first one right here, all right, we have ax plus b. If you have a linear factor in the bottom, and it is the only linear factor of that type, so just like we saw in that warm-up question, then we set it up like this, where we have a constant on the top and we have our linear factor on the bottom. So we'll have our constant over our linear, okay? Now, once in a while, we encounter a situation where the factor on the bottom is repeated, okay? So this is a situation where you might have a repeated factor, whereas the first one we would say is a non-repeated. Okay? So if you have a repeated linear factor, okay, if it shows up 2 times, then what we need to have is one linear factor, so a over ax plus b, and then we repeat the factor. So if it shows up a second time, we write the linear factor to a second power, and we need a different constant on the top, okay? And if that factor is repeated many, many times, then we keep going as many times as that factor is repeated. But the key thing here is that the numerator is going to stay a constant. It's not going to become a linear. It's going to stay constant, okay? So all of my numerators are constants. Now, this particular textbook does it as a sub 1, a sub 2, but you could certainly do it as like a, b, c, d. That's what I tend to do. I tend to use a different letter for each one, okay? So these first 2 are what happens if you have linear factors in the denominator. But once in a while, you're going to get to some situations where the denominator is actually quadratic. And more specifically, these quadratic factors are not factorable, okay? And so in that case, we have, again, 2 situations. You might have a non-repeated quadratic or a repeated quadratic. And with the non-repeated quadratic, all right, our denominator is going to be quadratic, but our numerator is going to be 1 degree less. So not quadratic, but linear. And just like the linear repeated factors, the quadratic repeated factors, I have to write out a new one for every repeat I have. And I keep going until I've gotten to the end of the repeat. Now, I think in the examples that I've chosen for us, both in the lesson and on the quiz, we're looking mostly at situations where that if it's repeated, it won't be repeated more than 2 times, okay? So I did want to give that as a heads up. I'm not looking for you to be able to do like things that are repeated to the 10th power, maybe just like 2 times, maybe 3 at the most, okay? All right, so just to kind of summarize, we can take a look at these 2 questions. After we factor our denominator, questions we want to ask ourselves are the factors linear or irreducible quadratic? So that word irreducible means that you cannot factor it anymore. So is it linear or is it irreducible quadratic? And then the second question we want to ask ourselves, is it a single factor or is it a repeated factor? And by answering those questions, that tells us how to set up our integral, okay? So let's get started with the very first case, which is non-repeated linear factors. So this is going to be very similar to our warm-up question where we were looking at a situation where we factor that denominator, see what we get, and then set up a system where we can cleverly choose values of x to find my a and b and c. Okay. So let's take a look at this. I've got my x squared over 4. I'm going to leave that the numerator alone for right now. And I look at the denominator and notice that it's cubic, but before I panic, I'm thinking, is there a greatest common factor? And there is. I can factor out an x, and then I'm left with 3x squared plus 4x minus 4 dx. Now, I want to see if I can continue to factor, okay? And so 3x squared plus 4x minus 4 does factor more. In fact, it factors into 3x minus 2 times x plus 2 dx. Now, this is actually another great place to pause and just make sure that you factored correctly, okay? So maybe FOIL it back out, make sure that you can get back to your original and that there are no sign mistakes, okay? So this is a good place to pause, check your work before you move on. Now, what this means here is that I hope that I end up with a situation that is like a over x plus b over 3x minus 2 plus c over x plus 2 dx. And if I know my a, and I know my b, and I know my c, then I can take the integral, okay? Now, all 3 factors that we had were linear, and they're not repeated. And so that's why I was able to put a constant on the top. So a for a constant, b for a different constant, c for a different constant, okay? All right, so now our job is to find our a, b, and c, all right? So we're gonna go ahead and write out this and set it equal to this. And save some space in between the fractions so we can just go ahead and fill in those missing denominator pieces pretty easily, okay? So we've got x squared plus 4 over x times 3x minus 2 times x plus 2 equals a over x plus b over 3x minus 2 plus c over x plus 2, okay? And so let's go ahead and fill in the missing pieces to make all the denominators the same. Now I tend to do that at the same time. So whatever I fill in the bottom, I also go ahead and fill in the top so that I don't forget to do it, all right? And so same thing here, this one needs an x and an x and an x plus 2 and an x plus 2. And this one needs an x and an x and a 3x minus 2 and a 3x minus 2. Okay. Do a quick visual check. Are all of the denominators the same? And if they are, go ahead and get rid of them. Okay. Now your job is just to work with the numerators. So we've got x squared plus 4 equals a times 3x minus 2 times x plus 2 plus bx x plus 2 plus cx 3x minus 2. Okay. All right. So we have 3 letters that we're looking for, A, B, and C. And let's think about what some letter or numbers might be good to choose for X, right? Who's got one number that might be a good one to choose for X?
2/3.
2/3. Yep, I see a 0. I see a 2/3. Yep, so we're gonna plug in 0 for one of them. It doesn't really matter which order you do this in, okay? 2/3 is another one. And then the last good number?
2. -2.
-2, yeah, -2, all right? So we'll give you guys a little bit of time to calculate this out and find what your values are for A, B, and C, okay? Now with that 2/3 though, I would really encourage you to work with the fraction. Don't turn it into a decimal and then round and then you're gonna get a weird number as an answer, okay? Keep it as a fraction, work with the fractions. It's okay to get fractional values for A, B, and C. All right, so take a couple minutes, find those values, and then we'll check those over and then move on to the calculus piece of integration. So hopefully we're getting A equals -1, C equals a 1/2. And then for B, I did want to just kind of show the fractional work. Okay, so we're plugging in 2/3. When we square a fraction, we have to square the numerator and the denominator to get that 4/9. And then when we add fractions, we need a common denominator, right? So the left-hand side becomes 40/9 equals B times, and this is going to be 16/9, okay? And so when we find our B value, we're going to have 40/9 times the reciprocal of 16/9. So 9/16. And when we reduce that, it should give us 5/2 for our B. All right. Any questions about finding A, B, or C? Okay. So once we find our A, B, and C, we're going to plug them back in to this part right here, and then we're going to be able to integrate, okay? So let's go ahead and shrink that a little bit. Okay, so I've got the integral of -1/x plus 5/2 over 3x minus 2 plus 1/2 over x plus 2 dx. Okay. Now, I think it was Mariah, you asked a really great question earlier about whether we need more than one dx, and I think this is a great place to kind of split it into 3 different fractions. You can write it split out, or you can kind of just imagine it in your head that you're splitting it into 3 different integrals. So what I mean by that is I'd have like negative the integral of 1/x dx plus 5/2 the integral of 1/3x minus 2 dx plus 1/2 the integral of 1/x plus 2 dx. Okay. And what I like about splitting it into different formats is that underneath each one, I can make a decision about what technique I'm going to use to integrate, all right? So it's a very purposeful decision. So when I look at this, okay, I see that this is going to just be a natural log, right? Because it's 1/x, and that is my one exception to the power rule. So when I integrate, I should get a natural log. Now, when I look at the second fraction, okay, this 1/3x minus 2, I know I'm going to get a natural log, but I also am going to need to use U substitution. All right. And last but not least, this is going to be a natural log, but I'm also going to need to use U substitution. So the U for the first one is going to be 3x minus 2. That makes my du 3 dx. And that 3 needs to get divided away so that I end up with this additional multiplying factor 1/3 in my answer, okay? So du/3 equals dx. Now, if we do the same thing for the second fraction, we'll let v equals x plus 2, dv equals dx. There's nothing I need to divide away for that last one, but if you get in the habit of never setting up the u sub, you're gonna miss the extra factor for that second one. Okay, so that second one is exactly the reason I want us to be thinking u sub. And you don't have to write it out every time. If the coefficient in front of x is 1, you're not going to need to divide by anything. But if the coefficient of x is not 1, then you'll have some sort of factor that you need to include. Okay. And so now we're just going to integrate each term. So the first one we already said is going to be natural log, but there's that minus sign in front. So negative natural log of x plus 5/2 times 1/3 the natural log of 3x minus 2 plus 1/2 times no factor, so natural log of x plus 2 plus c. And if we clean this up a little bit more, we'll have our negative natural log of x plus 5/6 natural log of 3x minus 2 plus 1/2 natural log of x plus 2 plus c. And that is our final answer. Okay. So in general, when you're looking at non-repeated linear factors, okay, so only for this case, when you're looking at non-repeated linear factors, you're going to end up with a whole bunch of natural logs in your answer, and that's okay. All right, so maybe let's go back up to our little table that has the different cases here. And in this case, you're going to end up with natural log, but you might need to use U substitution to get to your answer. Okay. All right, any questions about example number 1? All right, so let's move on to the case of repeated linear factors, right? So this one's already factored for you. What I'm interested in is the setup. Do we know how to set this up as our partial fraction decomposition, okay? So in this case, can someone tell me how many fractions I should have?
4.
Yeah, exactly. You're going to have 4 fractions. So the first denominator is going to be x plus 1. What's the numerator going to be?
What do you like? It's gonna be repetitive x minus 2 3 times.
Oh, I was just asking what the numerator was going to be. And someone said a, and that's correct. So it's going to be a linear numerator, right? What's the next denominator going to be?
X minus 2.
X minus 2, good. And that numerator is going to be b. Okay. What about the next denominator?
X minus 2 squared.
Perfect. X minus 2 squared. And the numerator?
C.
C. Beautiful. And the last one?
D over x minus 2 cubed.
Beautiful. Whoa. Not beautiful, Judy. There we go. Cubed dx. Okay. So I thought we would try one where we have a repetition 3 times just to kind of get the feeling of how we set them up. And I love that we remember from earlier that all of the numerators are going to be linear, or constants rather. So an A, a B, a C, and a D, all right? So let's go ahead and here's what I'm going to do. I know that when we look back at questions like this, like there's just so much writing that we're doing. So everything in the blue is just the algebra. We didn't even get to the calculus yet. And so what I do sometimes, and I think I do this on some of the answer keys, is I kind of, in my head, match all the denominators, and then I just don't write it out. Like I just write what's going to be in the numerator, if that makes sense. okay? So let me show you sort of the long way and then talk about what it might look like on an answer key. So the long way would be to write out your numerator and your denominator. Okay. And then set up your 4 fractions in this case and fill in the numerator and the denominator. So with the a times x plus 1, or a over x plus 1, I'm going to need x minus 2, and I'm going to need 3 of them. Plus, for the b, I already have an x minus 2, so I'm going to need an x plus 1. And how many x minus 2s do I need?
Squared 2.
Yeah, I only need 2 of them, right? So x minus 2 squared, x minus 2 squared, okay? So the goal here is not just to make a common denominator, but in fact to make the lowest common denominator or the least common denominator, all right? Anything more than that would still work, but you end up with things that are much higher powers and a lot harder to solve. All right. So let's continue. Plus c. C already has x minus 2 squared, so I need an x plus 1 and only one x minus 2. Okay. And then the last one, I am only going to need an x minus 1. Okay. So this is the long way. This is a whole lot of writing. And for some of us, I think it is important to show those extra steps. So I don't want us to shortcut this if we're not sure where all these things came from. But another way to kind of approach this might be to say, all right, look, I know I need a common denominator. So let me just write out the numerator. And let me see what each fraction is missing. So a needs x minus 2 cubed, plus b needs x plus 1 and x minus 2 squared, and c needs x plus 1 and x minus 2, only one of them, and d needs x minus 1, and that's it. Okay, so if you're feeling like I didn't really learn partial fractions really well, please show this first step for you, okay? I don't want you to kind of guess and be like, I think this is the right setup. But if you're feeling pretty confident with it, there's nothing wrong with jumping to the thank you. There's nothing wrong with jumping to that next step, and we do want to make sure we don't change any of those signs. Thank you. Okay. So from here, let's see how far we can get just by guessing numbers, all right? So it seems like we're pretty good with guessing numbers. I would say maybe a -1 and a +2. So why don't we try plugging those in, all right? So plug in x equals 2, see what we get, and let's plug in x equals 1, or -1, and see what we get, all right? All right, so when I plugged in 2, I was able to find D because all of the other ones went to 0, and I found D to be equal to 2. Okay. Now, when I plug in -1, I believe we get -54 on the left-hand side, so be really careful about your signs. And I believe we end up with a times -3 cubed. So that's going to give us -54 equals -27a, or a equals 2. Okay? Now, there's no other clever numbers for us to try because we have repeated factor, all right? So, if you get to a point where you're like, all right, that's it, I was only able to find 2 of them, but I have to find another 2, then what's going to happen at this point is we can just expand that right-hand side. Okay, we can go ahead and expand that right-hand side, and we're going to need to set up a system of equations, okay? All right, so what I mean by that is I'm going to keep the left-hand side, so 3x cubed minus 18x squared plus 29x minus 4 equals. And I'm going to go ahead and multiply this out. So x minus 2 cubed. And when I do that, I'm going to get a times x cubed minus 6x squared plus 12x minus 8. And when I FOIL everything out for the b term, I end up with x cubed minus 3x squared plus 4. And when I multiply out the c term, I end up with x squared minus x minus 2. And when I multiply out the d term, it's just d times x plus 1. Okay. Now, obviously, I did these ahead of time, so, take your time to FOIL things out, show that thinking, okay? But what we're going to do now is really just collect like terms, all right? So here's what I mean by that. 3x cubed would be considered a like term with ax cubed and bx cubed. So one equation we could write is that 3x cubed equals ax cubed plus bx cubed. But more often than not, we don't even write the x cubed, we just write it as 3 equals a plus b. Okay. Now from there, look at what happens. We already have our a, and so we can find our b. We can say that 3 equals 2 plus b, and so b equals 1. All right, so we've got one last letter to find. We have to find c. Now, it doesn't matter whether you pick the x squared terms or the x terms or the constant terms. You can use whichever ones you want. But I'm going to go ahead and use the x squared term. So negative 18x squared is going to equal negative 6ax squared minus 3bx squared plus cx squared. And I'm only going to write the coefficients. So negative 18 equals negative 6a minus 3b plus c. And when I do that, I've chosen a situation where I already know a and b, so the only number I don't know is c. So negative 18 equals negative 12 minus 3 plus c, or this gives us c equal to negative 3. All right, so we found our a and b and c and d. Sometimes we can just pick some numbers and then be clever about it, and then we get all of our constants. And sometimes we do need to do some more grunt work where we FOIL things out and we find some like terms on both sides and set up a system of equations, okay? So it's really useful to know both strategies. All right, now from here, let's go ahead and go back to our integral. So we have the integral of 2 over x plus 1 dx plus 1 over x minus 2 plus negative 3 over x minus 2 squared plus negative 1 over x minus 2 cubed dx. Now, when we do that, we can split it into our 4 different integrals, all right, and take our constants out at the same time. And some of us might be able to do this right off the bat, and that's certainly fine. You don't have to write the step that I just wrote. So maybe you jump right to 2, the integral of 1 over x plus 1 dx, plus the integral of 1 over x minus 2 dx, minus the integral of 1 over minus 3 times the integral of 1 over x minus 2 dx, minus the integral of 1 over x minus 3, x minus 2 cubed dx. Okay.
I have a question.
Sure.
I thought we said that d was equal to 2.
It is. So sorry.
Okay.
Let's put a 2 right here, and let's make that a 2. All better?
Yeah, thank you.
All right, and thank you, Omar. I appreciate your keeping me accountable for this. Okay, so now that we have our 4 integrals and we've double checked that we plugged in everything correctly, okay, we're gonna write down what strategies we might need under each one. So if I look at this first integral, what strategies am I gonna need to find that integral?
You just drop it straight into the natural log.
You could do the natural log, and I know we don't have to use the u sub because the coefficient of x is 1, but maybe just kind of for folks who are maybe missing that pattern, let's just write it down just in case, okay? Now the second one, I would say we could do the same thing, natural log and a u sub just to make sure we're not missing a constant, all right?
Is the d -2 or 2?
D is a positive 2.
Oh, okay, cool.
Yep. Plus 2. All right, there we go. Yeah, okay. All right. All right, so for the third fraction, 1 over x minus 2 squared, what rule are we going to use there?
Power.
Yeah, we're actually going to use the power rule. Exactly. Okay. We're going to use that power rule here. And so we're going to say not natural log, but power rule and a u sub just to kind of get in that habit of it. And then for the last fraction, we're also going to need the power rule and a u sub just in case there's ever a constant in front of the x, okay? All right, so I really like doing this step, and I've noticed from that first quiz that some of you seem to also find it helpful to sort of annotate like what you're doing as you do it. And I think, that idea of just being really active in your decision making about what you're going to use and why you're going to use it will definitely help you find success, especially as we kind of continue to layer on all different types of strategies. Okay. So let's go ahead and write out the u sub for these last two, all right? So my u in this third fraction is going to be x minus 2. My du is going to be dx. And that's actually going to be the same for all of them. That u, or, well, not that one. All right, so these will be my u and du's for the last three fractions, and this one, our u is x plus 1, and du is dx. Okay. So if we start to take our integral, we know that the first one will be 2 times the natural log of x plus 1. We know that the second one will be plus natural log of x minus 2. Okay. Minus, let's write out the u sub for the third one and the fourth one. So 3, the integral of 1 over u squared du, plus 2, the integral of 1 over u cubed du. And I think when we see it in that format, we can buy in a little bit more that it's not a natural log, right? So natural log is only when that power on the bottom is 0 or 1, and these powers are not 1. So if I integrate something with a power of -2, I'm going to end up with u to the -2 plus 1 is -1, and then the coefficient will be the reciprocal of -1, which is -1. Plus 2 times, if I have something to the power of 3, or -3, -3 plus 1 is -2, and the reciprocal of that is -1/2 plus c. And then our last step, just plug the u's back in, write it as a fraction, and then we are all done. So we've got 2 natural log of x plus 1 plus natural log of x minus 2 plus 3 over x minus 2 minus 1 over x minus 2 squared plus c. All right, so there we have our whole problem on one page. All right, so again, this decision making that we've been practicing the last 3 days is really important, because a lot of times we're going to need more than one strategy per problem. And in fact, even different terms might require different strategies. Okay, so if the annotations are helpful for you, definitely do that on your quizzes, because I think it just helps you mentally prepare for like a test and to study for all of those things. Okay. All right, so this seems like a good time for a break. It is 10:36, so let's be back at 10:41, and then we'll finish up with our last two examples here, which will deal with what happens when we have irreducible quadratic factors. Okay. All right, so I'll see you back here in like 5 minutes.
Hi, I have a quick question on the algebra.
Alrighty, so let's take a look at these last two examples. All right, so these last two examples are situations where you've factored as much as you can, and one of those quadratics is irreducible. Irreducible meaning several things. One, if you graph that quadratic equation, you would get a parabola that does not cross the x-axis, okay? So visually, if you graph it, it's not going to cross the x-axis. So for example, if I take a look at this x squared plus 4, I know that's a parabola and it's shifted up 4 units, but like this is the x-axis. So it never crosses the x-axis. That's one way to think about an irreducible quadratic factor. The other way to think about it is when you have an irreducible quadratic factor, what that means is it has no real zeros. So if you factor it, you could factor it so that it has imaginary components like i's, but that's not going to be useful for us in the realm of real answers, okay? So that's what we mean by irreducible quadratic factors. So when we take a look at this example right here, all right, we've got an irreducible quadratic factor in the bottom, the x squared plus 4, and then we have a linear factor. So you can have more than one type of factor in your denominator, and that's fine. And so our job is to make sure, first of all, that we set this up correctly. So I know that I'm going to have one fraction that has x squared plus 4 in the denominator. And I'm going to have another fraction that has a 2x minus 1. And for the irreducible quadratic factor, if I just put this, then I'm going to not get the right answer. Okay, so I don't want a constant there. I think about the quadratic and I say that's a power of 2. So 1 less than that power is going to be the top, ax plus
B.
Okay. Now, the next fraction has a linear denominator. And so that linear denominator means I need a constant at the top. Okay. All right. Now, it doesn't matter whether you choose to put the quadratic factor first and then the linear, or if you switch them, okay? Either way is fine. It's just that whatever's above the linear factor has to be a constant, and whatever is above the irreducible quadratic factor has to be a linear, okay? So the order's not going to matter. You should still end up with the same numbers for the same constants. All right, so let's try that shortcut that I was talking about in example number 2, okay? So by that, I mean, I'm not gonna write this whole long thing and then cross out my denominator. I'm gonna jump straight to that line where I only write the numerator, and then on the other side, I think about what those constants are gonna need to multiply to get the same denominator, okay? So when I write my numerator, I'm going to get x squared minus x minus 21. And I have the first numerator as ax plus b. And that denominator is only missing the 2x minus 1. So plus the second fraction is only missing x squared plus 4. Okay? So again, I only want you to use this step if you feel comfortable with it. Don't feel like you have to use this at the expense of maybe not really understanding where things are coming from, okay? So we've got our setup here now. Are there any nice numbers that we could maybe plug in for x?
1/2.
I could try 1/2, certainly could. Okay. Any other nice numbers?
No.
No, okay. And that's okay. And that's going to be something we encounter with the irreducible quadratic factors. And it goes back to what makes it irreducible. There's no number I can plug in to x squared plus 4 to make it equal to 0, okay? Now, at this point, it's really like solving these systems of equations is really up to you in terms of like what you feel like your strengths are. So for me, I look at this and I'm like, oh, I gotta plug in some fractions. So if I plug this in, I'm gonna get like 1/4 minus 1/2 minus 21 equals C times 1/4 plus 4. And it's like a lot of fractions. I mean, it's not a lot, but maybe more than I want to deal with at 10:45 on a Thursday morning, okay? So I could certainly solve this, and if I solve this, this would give me a value for B, all right? So if that is something that you choose to do, definitely go ahead and do that. For this problem, though, I'm going to revisit the other strategy we had, which is where we sort of FOIL everything out and then make some mini equations and see if that might help me avoid working with fractions a little bit, okay? So when I do that, I get x squared minus x minus 21 equals 2ax squared minus ax plus 2bx minus b plus cx squared plus 4c. Okay? And so what I'm able to do from here is have 3 mini equations. So I'd have x squared, or 1, equals 2a plus c. Right? Now, if I set up another equation with this negative x, I'd have negative 1 equals negative a plus 2b. And then if I set up a third equation, I have negative 21 equals negative b plus 4c. Okay. So sometimes we end up in a situation where we end up with a system of equations and they're not always so nice. So I just wanted to like do this one as an example of some strategies you could use when you're solving a system of equations, okay? So what I'm gonna do is I'm gonna solve this equation for C. So I get C equals 1 minus 2a. And then I'm gonna put that into this equation. So that's gonna make the bottom equation negative 21 equals negative b plus 4 times 1 minus 2a, or negative 21 equals negative b plus 4 minus 8a. And then I'm going to subtract the 4 to the other side. So negative 25 equals negative 8a minus b. And now what I can do is take this green equation and this black equation and use elimination to get rid of one of the letters. So what I'm going to do is I'm going to take that green equation and I'm going to multiply it by a 2. So I'm going to get negative 2 equals negative 2a. Nope, that's not what I want to do. Multiply it by a negative 8. Sorry. So times negative 8. That will give me 8 equals 8a minus 16b. And now when I combine the black equation and the green equation, I end up with negative 17 equals, the a's go away, negative 17b, and I get b equals to 1. All right. Now, once I have one letter, I think it makes it a little bit easier to find all the other letters. So now that I have my b value, I'm going to go ahead and plug that in. to this equation and get my a value. So -1 equals -a plus 2 times 1, or I get a equals 3. And now I have my a and my b, and so all I need
Where did you get x minus 8? I'm sorry.
x minus
8 on the next to the green arrow.
Got it. Okay, that says multiply the equation by -8.
Oh, multiply that. Okay.
Does that make sense?
Yeah, that makes sense.
Multiply by -8. Really good question though. I feel like it's weird to go back to like x being multiplication, but I did actually use that on the answer key, so thank you for pointing that out. So on the answer key for quiz 2, if I've multiplied an equation by something, I wrote like x as multiplication. I didn't write out the word multiply. Okay, so we've got our a and our b, so we're gonna plug that into here. Oops. To find our c. So c equals 1 minus 2 times 3, or c equals -5. Okay. Anybody getting a different answer for these constants? Let's check that before we go on. 8 times, where did the 4 come from in the negative? Oh, because it's 4c. So the equation says 4 times c. So then I multiplied 4 times 1 minus 2a. Okay, cool. All right, so we've got all 3 of our constants. Now we're going to plug them into our integral and do the fun part, which is the integration, okay? So my question now becomes the integral of 3x plus 1 over x squared plus 4 minus 5 over 2x minus 1 dx, okay? Now, if you feel more comfortable if you put a plus -5, that's fine. I tend to bring that negative sign out to the front when I can, but it's really up to you. So now let's split this into some more integrals and see how we can integrate, okay? So what we're going to do is we're going to take this first fraction, which has 2 terms in the numerator, and we're going to split it into 2 integrals. So the first one will be 3x over x squared plus 4 plus the integral of 1 over x squared plus 4. Okay, so these 2 came from that first integral, minus the integral of 5 over 2x minus 1 dx. Okay. So in the cases when we have a linear on top, it's often helpful to split it into 2 integrals, okay? And now each of the integrals is going to require a different technique. Super fun, right? So the first integral here, what technique should we use to integrate that?
U sub.
Excellent. We're going to use u sub, okay? And so in this case, u equals x squared plus 4, du equals 2x dx, and I'm going to go ahead and make that du over 2 equals x dx. Okay. Now, once I've done that as my setup, then what I can do is substitute in, Okay, so this integral will look like 3 over 2. All right, the 3 from here, and then the 2 because I divided from that dx, the integral of 1 over u du. Okay. When I integrate that, I will get 3/2 natural log of u, or 3/2 natural log of x squared plus 4 as the first part of my answer. Okay. Any questions on that first part? Okay. The second term is going to require a different strategy. Okay. So,
Extension.
what's up?
Extension.
Bro, your question, where did the +1 go? The +1 got split into this fraction. Okay. Now this, if you think back to yesterday's lesson, is one of the patterns we are looking at, but we don't need to do out the whole thing, okay? So this 1 over x squared plus something squared, I want us to be thinking that it's going to be arctan, okay? This is going back to when you learned about derivatives of inverse trig. Now we're sort of going backwards. We're integrating to get inverse tangent as an answer, okay? So with this, we want to identify our a, and a is not 4 in this case, but a is 2. And so the formula for arctan is 1 over x squared plus a squared. If we have this, then our integral will be 1 over a, the arctan of x over a. And so when we plug in what we have for our a, that's going to make this second integral 1/2 arctan of x over 2. Okay, so each part of our problem is going to require a different strategy, and that's okay. All right, last one here. We kind of return to what we learned in the first 2 examples, right? Where we know it's going to be a natural log, and in this case, we definitely have to keep our eyes out for the u sub. So u is going to be 2x minus 1, du equals 2 dx, or du over 2 equals dx. And so when I substitute that, I'll end up with negative 5/2 the integral of 1 over u du, which we know is our one exception to the power rule. And so we'll have negative 5/2 natural log of 2x minus 1, okay? So every single fraction required a different technique, a mix of u sub, some inverse trig, and natural log, okay? Now, those are, I would say, are like the most common ones, in addition to like the power rule with like if we have a u squared on the bottom or u to the third on the bottom. Those are the main techniques that we tend to use here. And so at the end, we just string together all the parts to get our answer. So we'll get 3/2 natural log of x squared plus 4 plus 1/2 arctan of x over 2 minus 5/2 natural log of 2x minus 1 plus c. Okay. Now you may encounter some websites or videos that show you or encourage you to simplify, like combining your natural logs. That's not something I'm looking for. So it's actually easier for me when I'm grading if you kind of leave it like this in separate integrals, okay? And just kind of, that's totally fine. Let's see, what question do we have? How I got the tangent. Okay, so if you think back to Calc 1, you learned about derivatives of inverse trig. So one of the derivatives you learned was that the derivative of inverse tangent of x is going to be 1 over 1 plus x squared. Okay, that's a rule that we know from Calc 1. What that means for us is that when we integrate 1 over 1 plus x squared, we should end up with arctan. Okay. The extension is just that sometimes our a value is not equal to 1, and so we need to think about how we compensate that in our integral. Okay. All right. So we've got this whole problem here. Case where we have an irreducible quadratic factor, only one of them. It sort of forced our hand to do a system of equations, and then at the end we ended up with 3 different types of integrals to integrate. Okay? All right, so we've got one last example to do, and so our last case that we're going to take a look at here is with repeated irreducible quadratic factors. Okay? So if we were to set up this as for our partial fraction decomposition, we would have one denominator that's x squared plus 1. And because that is a quadratic, my numerator has to be a linear. Now, just like the repeated linear factors, my next denominator needs to be x squared plus 1 squared. And that does not change the fact that my numerator here will also be linear. Okay? So let's go ahead and set up our numerators equal to each other and see what we actually need to multiply out. So my numerator is going to be 5x cubed minus 3x squared plus 7x minus 3 equals ax plus b. I need one more x squared plus 1. But what's really nice about this particular problem, I don't have to multiply that cx plus d times anything. I mean, really, I'm multiplying it by 1, but it already has the same denominator as the other side. Okay. Any questions about this setup right here? Okay. So I think this is a good case of when we can't even really pick clever numbers necessarily to find one of our constants right away. And so we, kind of like our last example, are almost forced to do a system of equations here. So let's see what we get. We're going to get ax cubed plus ax plus bx squared plus b plus cx plus d. And so we're going to have 5 equals a, oh, perfect, that's it. There's only one cubic. Okay. And then let's see what happens with the squares. -3 equals b. Okay, not so bad. All right, so now we've got 7 equals a plus c. So 7 equals a plus c, or 5 plus c. And so c is going to equal 2. And what do we have left? We have -3 equals b plus d. So -3 equals b plus d, or -3 plus d. So in this case, d is going to equal 0, right? And that's okay. That happens sometimes where one of your constants is 0, and you just plug the 0 in just like you would plug in any other number when you're setting up your fraction. All right, so let's get our constants into our integral and then see how many different integrals we're going to need to split it into. So I have 5x minus 3 over x squared plus 1 plus 2x plus 0 over x squared plus 1 squared. Okay. Now, we're going to borrow a strategy we learned from the last example, which is we're going to split this first integral into 2 separate integrals. So 5x over x squared plus 1 minus 3 integral of 1 over x squared plus 1, and then plus 2 the integral of x over x squared plus 1 squared dx. Right? So we end up with 3 different integrals here. Okay? I'd like to take a moment here and just give you maybe about a minute or two to identify what strategies you want to use for each integral, right? You're going to use u sub. Is it going to have a natural log? Is it going to be arctan? Do you need power rule? What do you need, all right? And take a moment to write that down, and then we'll go ahead and solve each integral. Okay. All right. Do we see any arctan that we might need?
Yes.
Yeah, which one? Which fraction?
Number 2.
Number 2, you got it. So this one, we're going to write down here that it's going to be an arctan, and we can even write down that A equals 1. Okay, so we can plug that into our formula in just a little bit. What about this first one here? What techniques are we going to need to use for the first integral?
U sub.
U sub, you got it. U sub, and are we going to use power rule or natural log at the end?
Power.
No, we're actually going to use natural log.
Natural log.
Okay, and the reason why is because our u is raised to the power of 1. Right? And so let's go ahead and do that one over here. U equals x squared plus 1, du equals 2x dx, du over 2 equals x dx. Right? So we're going to end up with 5 halves, because we take this 5 and this 2, bring them out to the front. The integral of 1 over u du. Okay? And so that's ultimately going to give us 5 halves natural log of u, or 5 halves natural log of x squared plus 1. Yes, Patrick, you can definitely take that 5 out beforehand. I don't know why I did it for the third one, but not the first one. Yeah. All right, and Omar, yep, you got it. That's the arctan for that middle one. So let's go ahead and do that one right now. All right, so this one is a pretty straightforward one because A is equal to 1. And so we just have 3 arctan of x over 1 if you wanted to write that, but you could simplify it to 3 arctan. Okay. All right, so we've got one last integral over here. We have 2 times x over x squared plus 1 over 2. And we've seen this before as well. We're going to need a u sub here. And this one, we're not going to use a natural log at the end because this power is not equal to 1. So we are going to need that power rule after we do the u sub, okay? So u equals x squared plus 1, du equals 2x dx, and du over 2 equals x dx. And so what that gives us in our integral is going to be 2 over 2, the integral of 1 over u squared du. Or if you wanted to take a step to write it as the integral of u to the negative 2 du, that might not be a bad idea to remember that you have to add the power of 1 to the negative 2, not a positive 2. And when we integrate this, we will end up with u to the negative 1, and then the coefficient is negative 1, which is going to give us negative x squared plus 1 to the negative 1, or negative 1 over x squared plus 1. Okay. So altogether, we ended up with 3 integrals. Each one used a different technique. And once we've done that, at the end, we just string them all together, and we've got our answer. So we've got a 5/2 natural log of x squared plus 1 minus 3. I'm going to bring down that negative because I lost it along the way. So negative, negative. Okay. So negative 3 arctan of x minus 1 over x squared plus 1 plus c. And that is our final answer. Okay. So one of the reasons that partial fractions come up again in Calc 2 is that if you're in this for the long haul and you're like a math major and you're going to be taking differential equations, they actually use partial fractions a lot to solve a lot of the questions in differential equations. Okay, so that's 255. The numbers that we get here for our constants, like our A, B, C, and D, will typically be nicer numbers, but I've thrown a few in the quiz that have not so nice numbers in preparation for, like, if you do go all the way to differential equations, more often than not, the numbers are not nice numbers, okay? So if you get a few fractions here and there in the quiz number 2, that's fine. Just, you know, be as diligent about checking over your work as folks have been holding me accountable for, so that you don't end up with the wrong sign or the wrong number, okay? All right, so folks, that's it for today's lesson. I'm going to go ahead and stop sharing my screen and pause our